Corrective shared autonomy is a method where human corrections are layered on top of an autonomous robot behavior. For example, in this cleaning task, the operator provides corrections to variables such as applied force and tool speed to clean paint off of a surface. An effective corrective shared autonomy system allows corrections across a range of state variables dictated by the needs of a given task. In this work, we present a method to automatically infer the nominal behavior, correction variables, scaling, and input mapping of a low degree of freedom corrective input. Our premise is that learning from demonstration is a logical way to infer these task parameters. Our method extracts admissible corrections using a per-frame PCA analysis of the demonstration data. Using this variance information, we are able to determine the most likely corrections, including coordinations of variables, at every time sample in the task. Depending on how the variance is distributed across the principal components, we propose two methods for operators to provide corrective input. If the variance is sufficiently described by a single principal component, we map the input directly to a mobile 1 degree of freedom haptic input. If the variance is split across multiple principal components, we use a grounded 3 degree of freedom input and determine the final corrective input by computing a best fit spatial mapping of the principal components. We also propose an override strategy for users to provide magnitudes of corrections outside of what was seen in the demonstrations. In general, users provide input by moving the input device away from a 0 point, similar to a joystick. In our override strategy, the input space of both devices is partitioned into two regions which are enforced by different stiffnesses of resistance. The first region maps input proportionally to the robot corrections. In the second override region, the input is integrated to allow for arbitrarily large corrections when necessary. We performed an initial evaluation of our system which consists of two surface cleaning tasks, both of which required removing a combination of marker and paint from a surface. The paint required more effort to remove than the marker. The first task was designed to contain one type of variance, a combination of force and increased tool speed to remove sections of paint. The second task was designed to contain two types of variance, force and tool speed to remove the paint, in addition to different levels of closeness to a nearby obstacle. We analyzed the results of the PCA analysis to show that the method generally extracted the expected corrections in each of the tasks. We also conducted a user study of the two proposed input mappings. For the single variance task, participants used a 1 degree of freedom haptic input. For the task with two types of variance, participants used a 3 degree of freedom input. For both inputs, users could reverse the execution as necessary by holding a button on the device. Participants used a variety of strategies, including preemptive corrections before sections with large amounts of paint, and posterior corrections, where the execution was repeated with more force and speed to address paint that wasn't removed successfully. We show that both input mappings had a system usability scale score in the top quartile of interfaces. We also show that in all cases, the inputs allowed users to effectively remove paint and marker from the surface. The nominal behavior alone was unable to remove all the paint and marker. In summary, we presented and evaluated a method to automatically extract the nominal behavior and required corrective input in a corrective shared autonomy system via learning from demonstration.